parametric form, we have the graph is the same shape, but we kind of know like some internals of it. We know that each spot on this graph corresponds to a value of t. So there is a t equals 0 spot on the graph, and a t equals 1 spot, and a t equals 2 spot. And we can even put an orientation on this graph in the direction where t is increasing. So we can put arrows saying that t increases going that way. And this is kind of information that the just x equals y minus 5 squared graph doesn't have. There's no orientation, no time or anything like that. So what we think of it, we often think of parametric curves as paths traced by a particle over time. So, the way we might imagine, so this one is, I don't know, I have a little particle, a little atom or something, it's floating around in space, and it starts here at t equals 0. It can be above, who cares? And time starts, and then it starts moving this way, and it crawls along, goes to here at t equals 1. So after 1 second, say, it's over here, and then it speeds up, and it gets to all the way to here in 2 seconds, and it goes in that direction, and it keeps speeding up, because at 3 seconds, it's going to be way out here, and 4 seconds, it's going to be out here. And so it's just something you can picture to go along with parametric equations, and in fact, it's often how they are used is to describe the path of something traveling over time. And so you can have different parametric equations that have the same graph, but then kind of different time and orientation. Different parametric equations, same graph, but different time, orientation, information. I don't know, I'll put it to you guys. Did anyone come up with a different set of parametric equations that has the same graph as this one that we've been looking at? It's worth a shot. How about this? So what's going to be the difference between this set of equations and the previous set? I mean, not the obvious difference. This one has a 2, the other one has a 2. I mean, like, in terms of time and orientation, how would you describe the difference? Yeah. All right, so the idea here is if this is a new particle, it's going to follow the same path, but it's going to go twice as fast. Just make a little table. Won't do too much there. T, X, Y, 0, you're at the same spot. But now at 1/2, t is 1/2. You're at the same spot where the other one was at t equals 1. You're at 1, you're at the same spot where the other one was at t equals 2. So it's like you're taking the same route, but you're going twice as fast. Questions? done parametric equations before want to tell me what graph this makes? Cosine of t. It's a circle. Exactly. Which kind of makes sense. Right, because if you go back to trig, remember your unit circle and everything, right? The x-coordinate is cosine of t, and the y-coordinate is sine of t. That's how you find your cosine and sine for given angles. So if x is cosine of t, y is sine of t, we get a unit circle. And it's oriented in a positive angle direction. And if we wanted to get rid of a parameter here, we could also by just saying, well, x squared plus y squared equals cosine squared plus sine squared g, which is 1 by trig identities. So x squared plus y squared equals 1 is the equation for this graph, which is the equation for the circle. It's all working out nicely. Okay, so what if how does x equal cosine 2t, y equals sine 2t different? What's the shape of this graph? Wide circle?
Yeah, it just goes, the radius is 2.
Radius is 2? How many people think yes on that? Who gets the buttons? A is yes, I agree.
Which one are we agreeing with?
That this gives us a circle of radius 2. Anything else is I disagree. Talk it over amongst yourselves. Figure out the right answer. Let me know.
It's not gonna get whiter, I don't think. It's just gonna go in circles and circles again. It's still gonna be 1.
The radius, I think the radius will still be 1.
Yeah.
It's just that particle's going to move around.
Yeah,
the circle
it's gonna
quicker.
move around
It's just
faster.
gonna shift the circle.
Yeah.
You're definitely, you're definitely first. Yeah, I know. Yeah, I think we would shift.
'Cause it's not going to be, it's not 2 cosine of t.
Yeah, exactly.
So,
Exactly.
Doubling the interval between the two. Yeah.
that's kind of right.
Yeah.
Because there's no way we can do something as trivial as, oh, we multiplied by 2, it's going to be twice as big.
It's now where it was. You had A or 3, put your answer up.
With the radius of 2.
same circle 2 times as fast. Let me say too, I was talking with a few people who are doing the problem and going like, I don't know, I remember something from here and this and that, maybe I use my calculator, and that's all fine and good, but don't forget that you can always do just the simplest, most straightforward thing. Just plug something in. If you plug in t equals 0, that would tell you if this is true or false right there. That's all you have to do. If you plug in t equals 0, you get x is 1 and y is 0. So it's not a circle of radius 2. But yeah, so what it is, it's a circle that, it's twice a circle. Because you go around, this is t, or it's, you go around over and over again, but you go twice as fast. All right, any questions? Okay. So, next, can we turn what's called regular curve into parametric? So I have a function and I want parametric coordinates for this function. And I'll tell you the answer to my question is yes. And the further answer to it is yes, it's really easy. You can do it. Yeah.
X equals T.
Yep. There. For parametric. I don't really have much more to say about that. Any questions? Really? Yeah. Yep. straight line, okay. What line? It's a line. You should be able to give me the equation for it. Anyone eliminate the parameter and solve? Yeah?
1 plus 2 times x minus 3 over 5.
That's what you said?
Yeah.
All right. It's a line, it's this line. We could have gotten this by eliminating the parameter. Okay, so what should we know? The slope of this line is 2/5. We do another one of these, it's enough to see the pattern. It's 2/5 because it's 2/5. The line also passes through. Are you sure it's? Yeah. 3, 1. Hold on, I have to work that myself. Yeah. All right.
Did you plug in 0 to get 3, 1? Did you plug in 0 for
Zero,
t?
Yeah. Oh, no. 1. At t equals 0. So a line, the parametric form of a line is something you might want to just learn to recognize, and you can read off facts about the line pretty quickly. Yeah, we're going to talk about that. Any questions? All right. So someone did this on their calculator, which everyone know you can graph parametric equations in the calculator. If you don't, learn how. It's helpful. And they got a shape like this, and it was, and went like that, and then it just stopped at that point. And why did that happen? Yeah.
In the Windows thing, the t sets at 0, so they have to change it to a negative value for it to go more than that.
Right. Okay. So often we restrict the values of t. So we might say like I want x equals cosine t, y equals sine t, and t is between 0 and 2 pi, so that I only get one loop around the circle, not an infinite number of loops. In this case, in the case above, t is restricted to t greater than or equal to 0, so anyway, that's just a setting you have to change your calculator. You can use your calculator. Any questions? Yeah. How do you graph? I honestly do not remember how to graph on a calculator. Here.
If you do something
And then,
The mode.
and then it says function, and then it's VAR parametric.
Okay. Mode function, then choose parametric, and then you can enter stuff, I guess. Thank you.
Something nice to know.
All right, but this is the rest of this course, and we have done any calculus yet. We haven't talked about rates of change or integrals or anything like that. So we have to do a little bit of calculus with parametric equations. And all we're really going to do is derivatives or tangent lines. So tangent line. Right there. Right, because we have a curve, so this curve has a tangent line, so that tangent line has some equation, so how do we figure out that equation? So let's see how to go about it. Let's say we have gradients, x's, whatever, f of t, y or g of t. And suppose we're going to do a little trick here. We're going to imagine that y is a function of x. It might not be, but this is just kind of a trick to kind of see where the formula comes from. Then the derivative of y with respect to t. Well, y is a function of x and x is a function of t. So in this case, this would be like the derivative with respect to t of the function y of x of t. And so we have change rules, right? Y prime of x times x prime of t. In other words, we're talking dy dx times dx dt. Now if dx dt is not equal to 0, then we can divide by it, and we get that dy dx equals dy dt divided by dx dt. Yeah,
How can we make that assumption? Suppose we imagine that y is the function of.
we can't really. So this is not a proof of anything. This is just kind of a,
Example.
yeah,
I guess
simple,
it's-
intuitive reasoning type of deal. I can try and do more proof, and I will if I have time. But, so, in any case, this kind of makes sense in various ways. You could think about it if you like, as, oh, if you cancel the dt, you get this, so that's a way to remember the formula. And you could think, well, you know, to find the slope at some point, it's like, how much is the y changing? dy dt divided by how much is the x changing? dx dt. It all makes sense. But let's actually use it in some problem somewhere. Okay. So, let's do an example. X cosine 5t, y is sine 3t. Anyone know what this looks like? Oh, good. I'd be surprised if you did. Let's graph. All right, so obviously these are not easy to graph just by staring at equations in general, but you know you have computers and all this. So here's this function for s instead of t here, between 0 and pi over 6, and we can just kind of step it up little by little, and then curves back on itself. Maybe, I don't know, pi, and it starts getting crazy, and you go to 2 pi, and it's really cool. You can get cool stuff with parametric equations. So, you know, you're not going to be able to write this as x is a function of y or y is a function of x or anything like that. Just do derivatives the normal way. dx dt, which is simple. Negative 5 sine 5t. We're going to need dy dt, which is 3 cosine 3t. And let's say I want to know what is the tangent line at some nice point that works out nicely. At 1/2 0, which this graph goes through. Right, so let's get rid of some of this. It goes through 1/2 0. We want to know the slope of the tangent line at that point. Okay. So in order to figure that out, first we need to know what the t value is for that point. Anyone figure that out? Here are your equations. Zero, y equals 0. So sine of 3t equals 0. Ideas? T could be 0. It would give y equals 0, but that would give x equals 1. Alright, you guys play around with it using calculator or whatnot. T, pi over 3 work? Yeah. Pi over 3, then yeah. Cosine of 5 pi over 3 is down there at 1/2. Okay, so anyway, find the t, then dy dx is negative, no, is 3 cosine 3t divided by negative 5 sine 5t, and so dy dx at t equals pi over 3. This is 3 times the cosine of pi of negative 1 over negative 5 times the sine of 5 pi over 3, which would be negative 3 over 2. So we negative 6 over 5 root 3. So the equation of the tangent line then is y equals negative 6 over 5 root 3 x minus 1/2.
How do you get pi over 3 again?
So you could with the chart solve and find where sine of 3t equals 0 and cosine of 5t equals 1/2. So you solve each one of these individually and compare the solutions.